Now in this session we are going to see the concept of resonance and effect of damping in the case of oscillations, and also we see the Helmholtz resonator. Now we see the concept of resonance. What is a resonance? In the previous session we have seen the forced vibrations, in which when P is equal to omega, the amplitude is maximum. That condition is called as a resonance. Resonance is a phenomena when the frequency of periodic force acting on a vibrating body is equal to the natural frequency of vibrations of a body. The energy transfer from the periodic force to the body becomes maximum, because of which the body is thrown into a state of wild oscillations. What exactly is happening is, you can see the tuning radio when you are operating in your mobile. If a station is set at 93.5 FM, if your mobile set, the frequency of mobile set and the transmitting frequency, if it is near, then only you can hear the sound at the station. That is because of the resonance. When the frequency of the transmitting station and the frequency of your mobile set matches, then only you can hear the loud voice of sound. So this is because of the resonance. This is the best example for resonance. Similarly here, when the frequency of periodic force acting on a body is equal to the natural frequency of vibrations, then there is an energy transferred and the amplitude is maximum and you can hear a loud voice. So this phenomena is called as a resonance. And I told you, amplitude of vibrations reaches maximum at resonance when P is equal to omega. P is nothing but the frequency of the applied force is equal to the natural frequency. P is equal to omega. So the examples are nothing but a radio receiver set tuned to the broadcast frequency of the transmitting station. That is what I told you. The radio receiver set, that is your mobile, when you set the frequency for 93.5 means if you go with 93 you cannot hear. If you go with 94 frequency you cannot get. Only if it is exactly 93.5, then the broadcast frequency of transmitting station and the receiver set of your mobile, the frequencies match and there will be a large amplitude where you can hear the voice. So this is the best example for resonance. Even the Helmholtz resonator is also an example. Setting up of standing waves in Meldis experiment. These three are the examples of the resonance. Now we see what are the conditions for the resonance. Now here there are two conditions based on the equation 11 which we have seen in the forced vibration. See, this is the equation for, this is the equation. A is equal to F by M into root of 4B square P square plus omega square minus P square whole square. This is the equation 11 which we have derived as equation for amplitude, for equating the coefficients of sine and cos functions, and if you divide those two equations you will be getting the equation of amplitude, which is equation 11. Here B is nothing but R by 2M. From this equation, what are the cases for which amplitude is maximum? When amplitude is maximum means the denominator should be minimum. What are the cases where the denominator will be minimum to get amplitude as maximum are nothing but the conditions making R by 2M as minimum. As I told you here in these two terms, if you make this term negligible and this term negligible, the amplitude becomes maximum. Here in this we know that B is equal to R by 2M. If R by 2M is set to minimum, what will happen? The damping caused by medium is made to be minimum. This is the first condition. When R by M is minimum, that is damping caused by medium is made minimum. This is the first condition. When damping is made minimum, this quantity becomes minimum value. When this is minimum value, the denominator is reduced, so amplitude becomes maximum. So this is one of the condition. Also, by tuning the frequency P of applied force is equal to the natural frequency of vibrations of the body, then as I told you, P is equal to omega, this term goes away. So this is set into minimum, thereby amplitude goes to maximum. You remember here, when the denominator is made minimum, amplitude numerator becomes more. So these are the two conditions where R by 2M is minimum and making P is equal to omega. These two are the conditions to have a maximum amplitude based on this equation. So A is maximum, denominator must be minimum. That is what I have explained. So this is the basic condition to have a resonance. Two conditions, B is equal to R by 2M is minimum and P is equal to omega. So damping is minimum when P is equal to omega, A becomes A maximum. That's what. When P becomes maximum, when damping is minimum means P is equal to omega, A becomes A maximum. So substituting the values over here, A becomes A maximum, F by M and 4B square into omega square is equal to here applying this part, what happens to this part? This omega square minus p square is nothing but this one here. Here when a is equal to equation from equation 11, 4 by m into 4b square, b is equal to r by 2m. If you take that, you will be getting this as equation. So a maximum is equal to f by m into 2b omega. This is the expression for the maximum amplitude. Next is the sharpness of resonance. What is meant by sharpness of resonance? It is the rate at which the amplitude changes corresponding to the small change in the frequency of the applied external force at resonance. That means at resonance, if the small rate of change of frequency, when there is a small rate of change of frequency, how well the amplitude is changing. It is the sharpness of resonance is the rate at which the amplitude changes corresponding to the small change in the frequency of the external external force at resonance. So what exactly is happening here is, when you can see when you tune your mobile set with the frequency, say suppose 93.5 FM, if you change it from 93.5 to 93.3, what is the amount of amplitude changes? And if it is 93.8 FM, 93.8, what will be the change in the amplitude? That is when there is at resonance, that is 93.5 at resonance, if there is a small change in the frequency 93.2 or 93.8, what will be the amplitude changes? It is the rate at which the amplitude changes corresponding to the small change in the frequency of the external applied force at resonance. This is called as a sharpness of resonance. When the frequency applied force is equal to the resonant frequency, steep increase in amplitude of vibration is observed as peak. This peak decreases rapidly as applied force starts deviating from the resonant frequency. That is what. At 93.5 only you will be able to hear the large sound. If it is 93.2, you may not be able to hear clearly, and at 93.8 also you may not be able to hear clearly. So this is the sharpness of resonance. Significant. What is the significance of sharpness of resonance is the rate at which the change in amplitude occur near the resonance depends upon the damping. For small damping, rate is high, resonance is sharp. For heavy damping, rate is low and resonance is flat. So sharpness of resonance is defined as a change in the amplitude to the change in the frequency, that is f by m by 2b p omega. This is the sharpness of resonance. Next, what is the effect of damping on the sharpness of resonance? So you can see here the graph is peak. Lightly damped means graph is peak when b is small. Heavily damped means b is large. And this is undamped. We do not know. For b equals to 0, the peak is somewhere. So it is for a lightly, when b is small, peak is more, and b is large, peak is blunt here. So this is the effect of damping on the sharpness of resonance. The graph shows the variation of amplitude with respect to the damping. The maximum amplitude at resonance is a function of damping. You can see here as a function of maximum amplitude is a function of damping. Higher the damping, lower will be the amplitude. You can see here, higher the damping will be amplitude. Higher the damping, lower will be the amplitude at resonance. Higher the damping, lower will be the amplitude at resonance. Higher the damping. See here, damping is more. Higher the damping will be, lower will be the amplitude at resonance. This is the at resonance means this is at resonance. Sharpness will be higher for lower damping. Sharpness is more, peak is more for lower damping. Lower damp, peak is sharp. Sharpness will be high when the damping is small. Curves are flat for larger value of b. That is what I have told you. Curves for b is small means curves are p. Sharp resonance. b is small means sharpness is more. When b equals to 0 shows split in amplitude indicates infinite value. For amplitude at resonance, a special case which never exists in reality. So curves are flat for larger value of b. Curves are flat. Here see, you can see curves are flat for larger value of b. See, this is the effect of damping. Now you can see the examples of a resonance. Examples of resonance is mechanical resonance. It is nothing but a Helmholtz resonator. It is an instrument used to detect the presence of sound of a particular frequency in the mixture of sound of different frequencies. Now the construction, it consists of a hollow metallic sphere with a cylindrical long neck A and a fine hole B opposite to that of A. This is a resonator construction, resonance mechanical Helmholtz resonator. where this is A, it consists of hollow metallic sphere with a cylindrical line. This is entry is A and the exit is B. Now the air inside the sphere has a definite natural frequency which is omega. Now we see the working of it. The sound of different frequencies enter the sphere through A. That means sound of different frequencies enter the sphere with a different frequency. Different frequencies enter the sphere through air. The air in the resonator. Now here when the sound of different frequencies enter the sphere through A, the air in the resonator resonates for the frequency of the sound which is equal to the natural frequency of the air, producing a resonance which can be heard as a loud sound at the end B. That means the Helmholtz cannot resonate for any other frequencies. For whatever the frequency it is set with an omega, for that frequency, the frequency of the input and the frequency of this one, if it becomes, then only the Helmholtz resonator gets a sound. That means it is taking from a different values of frequencies. When the frequency of this, it is omega, in which there are multiple frequencies through which it is entering. When the frequency of the input frequency is equal to the natural frequency of this, the resonator will vibrate. So these are so V is nothing but a volume of a resonator and omega is a natural frequency of oscillation. Therefore, we can say that the square of natural frequency of oscillation is inversely proportional to the volume of a resonator V. So, omega square is proportional to 1 by P, or omega square is equal to K by V, where K is constant. Therefore, omega square V is equal to K. Thank you.